Hello, my esteemed viewers. You're welcome to this channel, Medical Science Lecture Room. Here we try to keep you informed on science and medical matters. At the comfort of your living room, you can learn medicine and science from this channel. Once again, my name is Dr. Godwin Obono, and today's discussion will be on chemistry. The topic is dative covalent bonding. I have done a video on ionic bonding, covalent bonding. Please check for those videos so that you'll be able to combine our understanding with what you may learn from today's discussion. Let's begin. Dative covalent bonding is a type of covalent bonding. Normally, chemical bonding is divided into ionic or electrovalent bonding and covalent bonding. And the covalent bonding is further divided into ordinary covalent bonding and dative or coordinate covalent bonding. Today, we will be discussing coordinate bonding. I will be looking at the difference between dative covalent bonding as well as ordinary covalent bonding. Generally, covalent bonding is a sharing of electrons between two atoms of almost the same electronegativity. Unlike ionic bonding, where there is transfer of electrons from one atom, metallic atom, to the other atom, the non-metallic atom, leading to the formation of what? A positively charged cation and a negatively charged anion. But in dative covalent bonding, we have is a type of covalent bonding because it involves sharing of electrons. But the only difference here is that the electrons that are being shared will come from only one of the participating atoms. What that means is that the shared pair comes from only one of the participating atoms. Unlike in ordinary covalent bonding, where the shared pair has electrons that were contributed equally by the participating atoms. But in dative covalent bonding, it is only one of the participating atoms that will contribute to the shared pair, as you will soon see. Now, for you to have a better understanding, let's quickly take example, or let's quickly describe dative covalent bonding in some compounds. For example, let's take the formation of hydrated copper 2 ion. Bonding in hydrated copper 2 ion. When we say hydrated copper 2 ions, it means that we have a combination of water, because hydrated here is a word that represents water. So we're having a case of copper 2 ions plus water, and now that will give us copper 2 ions plus water. That gives us this one you have. That means we have 4 molecules of water. We have 4 molecules of water combining with copper 2 ions. Why is it 4 molecules? Please listen carefully. Copper, in this case, copper 2, for copper to exist as 2 plus, it means that copper has given out its valence electrons. And for it to have been given out its valence electrons, it means that copper has no electrons on its outermost shell. Now, copper wants to become stable. Remember, the reason for bonding is what? Stability. Every atom wants to be stable, either wants to attain its duplex structure or octet structure. For copper wants to become what? Completely filled with what? 8 electrons in its outermost shell. So for it to exist as 2 plus, it means that copper has no electrons on its shell. That means copper outermost shell is just empty, nothing is there. Now, for it to get through, for copper to now have 4 electrons on this outermost shell, it wants to now go into dative bonding. Remember, in dative or coordinate bonding, we said that only one of the participating atom or participating molecule will contribute to the shared pair. So the electrons that will be shared in this case will come from only water. It will not come from what? Copper, because copper doesn't have anything. So for electrons to be shared, remember, this is sharing. Electrons have been shared. In dative covalent bonding or in covalent bonding, there is sharing of electrons. The only problem here is that the electrons have been shared will not come from copper, because copper doesn't have any electron in its outer shell. Rather, the electrons that will be shared will come from what? Water. Now, for water to have electrons to share with copper, water must have an excess of these electrons. That's why for such a molecule, any molecule that must undergo dative covalent bonding, that molecule must have what we call lone pair. Lone pair are electrons that are not used in bond formation. Any molecule that doesn't have lone pair cannot undergo dative covalent bonding, because in dative covalent bonding there must be a participating molecule or a participating atom with an excess electrons. He has it in excess, and so he wants to share those electrons. That's why water is an example of that. Why do we say water has a lone pair? Now, if you look at the structure of water, now basically water has this is the structure of water. It has oxygen. This is oxygen. Supposing I say this is oxygen. Oxygen normally is 6. That's why I say look at the video on covalent bonding. That video will help you understand ordinary covalent bonding. Now, because that's exactly what we want to apply here, that understanding. Now, this is oxygen. Now, this oxygen, I want to write the structure of water now. This is oxygen. Normally, oxygen has atomic number of what? 6. If it has atomic number of 6, the inside will be what? The inner shell will have what? A total of 2 electrons. The outer shell will have what? 6 what? Electrons. So, if I come here, I put 2 here. Look at what I've represented. I've represented 6 electrons, 2, 4, 5, 6. 6 electrons on the outer shell of what? Oxygen, and then 2 electrons inside the inner shell of what? Oxygen. Now you now have water. Normally, let's forget this 4 first. Normally, you now have 2 hydrogen atoms. The 2 hydrogen atom, one will come here and connect itself. Now you see this other electron belongs to what? Belongs to this hydrogen, and this other hydrogen will come here and connects itself with its own what? Electron. So each of these hydrogen, this is hydrogen, and this is what? Hydrogen. Please remember that there are 2 electrons here. You can see that one of the electron here, this electron came from this hydrogen. This one belongs to the oxygen. For here, this one belongs to this hydrogen, the other belongs to what? Oxygen. And you know that this is also what? A covalent bond that will be formed here. That's why it is written like this. It is written like this, where this represent these 2 electrons, this represent these 2 electrons, and then you have this oxygen. Now you now see that these 2 electrons are not involved. So because they are not involved, we can write them here, and you write them here. You say that these 2 electrons that are not involved are called the lone pair electrons. You see, remember that this on the outermost shell of oxygen, we had originally 6 electrons. Those out of the 6 electrons, 2 have been used to share with this hydrogen, and they have also been used to share with this other hydrogen. That means 2 of the electrons that are on the outer shell of oxygen have been used. Why? Out of the 6 that were there, 2 have been used, but 4 have not been used. Those 4 that have not been used are now called lone pair electrons. And these are the electrons. These 2, there are 4. So 2 of them constitute a pair. The other 2 constitute another pair. That's why we said lone pair. There are 2 lone pair that you have in water. Now, without water having this excess electron, it is these excess electrons that represent what that we call lone pair. If water do not have these excess electrons that are valuable for another atom to share, then water would be able to combine with what? Copper. So because of this feature or these characteristics of water, that's why water is able to combine with its copper, because copper doesn't have anything. Its outermost shell is empty, yet it wants to become stable. And so because it wants to become stable, copper must look for another molecule that has that thing it's looking for, which is electron, that has it in excess. And you find that in molecules with lone pairs, like I have described for water. Now, as a chemistry student, you need to look for molecules with lone pair. One example is water. We also have ammonia. Now, you now say this is water. This is a molecule of water, just one molecule of water. We now say now 4. We place 4 here. That means there are 4 of this. 4 of this. So 4 of these. Now what you now have here is that at the end, the product is this. Now this is your copper that has, this is your copper that has nothing. This is your copper that has nothing on this outer shell. Now this water, because there are 4 of them, one of the water will come and connect itself here and donate or share its electron. It's not donating, it's sharing this electron. Remember that this water, there are 4. Each of them will come and use either of these two, and this arrow tells you that this water is bringing 2 of this, either brings this 2 or it will bring this 2. But the idea is that each of the water will bring 2 of this. And so as it brings 2, the other water will come here, and also that's why there is an arrow. This arrow is not telling you donation, but it's simply telling you that the electrons that are shared come from what? Water. And then you have another one here. That's why we have 4 molecules of what? Water. You have that. So if 2 electrons from this water, 2 from this water, 2 from this water, 2 from this water, you now have a total of what? 8 electrons on the outermost shell of what? Copper. In that way, copper has become what? Stable. In that way, copper has become stable. So this is what we call copper 2. Now, when you have written it that way, now the charge that copper has, remember that copper has 2 plus, must always be written on top. Please don't forget the charge on the copper on what? This atom that doesn't, or the ion that doesn't have electron, whatever charge it carries should be written on top. Because sometimes you see that in exam. So if it is, this is 3 plus, 3 plus should be written here. So please take note, this is what we call hydrated copper 2 ions. Hydrated copper 2 ions. Now you see this again in copper 2 tetraamine ion. Copper 2 tetraamine ion. That's another example. Now it's similar to this. If you check your books, you see it. Now, but please, the idea is that in this case, I repeat myself, that the bonding is done in such a way that one of the participating atoms does not have anything to contribute. It has its empty outermost shell to be what? Empty. But the other one has excess electrons in the form of lone pair, and that's the one that is ready to share electrons with the one that doesn't have. At the end of the day, you see common example of dative covalent bonding. You see it in what? The formation of copper 2 tetraamine ion. You also see it in what? Hydrated copper 2 ion. The explanation for copper 2 tetraamine ion is similar or the same with this one. Okay, now let's see copper 2 tetraamine ion. The formation of copper 2 tetraamine ion. The formation of copper 2 tetraamine ion. Now again, in this case we have copper plus ammonia. Ammonia, that will give you copper, and then you have ammonia here. You have ammonia here. Like I said, the charge here must be 2 plus. So again here will be 4 atoms of what? Ammonia. 4 moles of what? Ammonia. So this is equally the same explanation. The same explanation for copper 2, hydrated copper 2 ion applies here. The only difference is that here we are using ammonia, while the other one we use water. But the explanation is what? The same. Now, what I may add here is how the bonding in ammonia is. How did ammonia? The question is that does ammonia has a lone pair? Because for ammonia to bond with this datively or coordinately, ammonia must have a lone pair. The question is that does ammonia has a lone pair? For us to answer that, we will quickly say, okay, what is let's see how ammonia is like. Remember, ammonia, the central atom in ammonia is it's nitrogen. What is the atomic number of nitrogen? It's 7. The atomic number of nitrogen is 7. Now, if you draw this, if you draw this, you say 2 will be inside, 2 electrons in the inner shell. Then how many electrons do you think will be on the outer shell? 5. So I have 1, 2, 2, that's 4, 5. You see, we have here 5 electrons. 5 electrons on the outer shell and then 2 in the inner shell, giving you a total of what? A total of 7 electrons for what? Nitrogen. Now, ammonia has, ammonia is a combination of nitrogen and what? Hydrogen. Nitrogen and hydrogen. They are what? We have 3 atoms of hydrogen. So one of the atoms of hydrogen will come here and bond with ammonia. The other one will come here and bond with ammonia. The other will come and bond with ammonia. So you cannot see that this is hydrogen, this is hydrogen, this is hydrogen. Please take note that the 2 electrons you see here, one is from hydrogen, the other belongs to what? Nitrogen. This again, the 2 electrons you find here, one belongs to hydrogen, one belongs to what? Nitrogen. The same applies to here. So you cannot see at the end. Remember, this I have done is ordinary covalent bonding. This is a bond. This is a bond. That's why we always will represent it as this. It's always represented this way. The formation of this one is ordinary covalent bonding, ordinary covalent bonding, ordinary covalent bonding. Now it means that through ordinary covalent bonding, you have ammonia molecule. Now the ammonia molecule now go into dative covalent bonding to stabilize copper 2 ions. Now when you have done this, you notice that after you have done this, you are left with 2 electrons here. These 2 electrons are not used in the bonding. Look at them. The 2 electrons are not used in the bonding. These 2 electrons were never used. They were never used in the bonding. These are the 2 electrons that you described to be one lone pair. That means ammonia has 1 lone pair, but water has what? 2 lone pair. Very important to know. Please take note. Ammonia has 1 lone pair of electrons. It therefore means it has 2 lone pair electrons, while the oxygen has 2 lone pairs. Therefore, it has 4 electrons that you describe as one lone pair electrons. Please take note. It is this property of water and ammonia that makes them the commonest molecule that can undergo dative covalent bonding with a participating atom that has no electrons in its outermost shell. Please, that is the basic difference between covalent bonding and dative covalent bonding. In covalent bonding, we said that the participating atoms contribute equally to the shared pair. But in dative covalent bonding or coordinate covalent bonding, only one of the participating atom or molecule will contribute to the shared pair. And that one must have excess electrons in the form of what? Lone pair electrons. At this point, I want to believe you have understood. But if you have any problem, please don't fail to drop your comment on the comment section. Don't also fail to subscribe to this channel. Also, like this video, share this video. Again, let's not forget the properties of covalent bond. The properties of covalent bonding. Please take note. When we discuss ionic bonding, we identify 3 properties, basic properties. We talked about high melting and boiling point. We talked about solubility. We talked about conductivity. But for covalent bonding, they are not soluble in water. They are rather soluble in what? Polar solvent. For covalent molecules, or the product of what covalent bondings are what molecule? They are not conductive, and if they are not conductive, it means that they cannot be used as what? Electrolyte. Please, more questions, any question, drop them at the comment section, and don't fail to go for other videos of this channel. We have a number of these videos, and if you have any problems, there is any video you want me to do for you, any question, please don't fail to do so. Or drop them at the comment section. I will respond. Thank you.